Okay, this is problem one. We let p and q be real numbers and let f be the function defined by this piecewise function that is connected at or broken up at x equals 1. Find the values of q. First of all, we're trying to find the value of q in terms of p for which f is continuous at x equals 1. So in order for the function to be continuous, then the value of the function from the left has to equal, or the limit of the function from the left has to equal the limit of the function from the right has to equal the value of the function at x equals 1. And that's what I have shown here. The limit from the left has to equal the limit from the right. As we approach 1, it has to equal the value of the function at f at x equals 1. Now, since the left branch and the equal sign are the same function, so we really don't have to worry about the last part of that. We just need to show that the limit from the left is equal to the limit from the right. And since what we're really doing here is just direct substitution with x equals 1 for the left branch has to equal direct substitution for x equals 1 from the right branch. And so what I've done is I've substituted 1 for x everywhere in the left branch. And you should see what's going to happen. Those 1 minus 1's will all zero out. And so all I'm really going to be left with on the left side of this equation is 1. Now on the right side, I use the right branch of the branch from x is greater than 1, and I plug in x equals 1, and I wind up with q plus p. What this gives me then is 1 is equal to q plus p. What I'm asked to do is find the value of q in terms of p for which f is continuous at x equals 1. And that would be that q is equal to 1 minus p. And that's my answer for A. For part B, we want to find the values of p and q for which f is differentiable at x equals 1. In order for f to be differentiable at x equals 1, then the derivative, the limit of the derivative as we approach 1 from the left has to equal the limit of the derivative as we approach x equals 1 from the right. And it sets up almost exactly like we set up the limit above, except that we're working with derivatives this time. And so I need to take the derivative of the left branch. And the first thing I do is up in the function definition, I expand out the left branch. And from that, I would just take the derivative or find the derivative using a series of power rules. And the derivative from of the left branch then as x approaches 1 is going to be the derivative of 1 is 0. The derivative of 2px is 2p. The derivative of negative 2p is 0. We're assuming that p is a constant here, not a variable. The derivative of x squared is 2x. The derivative of negative 2x is negative 2. And the derivative of 1 is equal to 0. On the right branch, the function is qx plus p. That's a linear function, so its derivative is just the slope of that line, which is just q. And remember, we're still taking the limit as x approaches 1, so I'm just going to plug in x equals 1 only into one place, into the 2x, and that gives me just 2p equals q from that. Now since we know that q is equal to 1 minus p, we now get 2p is equal to 1 minus p, 3p equals 1, p is equal to 1/3. Since q is equal to 2p, then q is equal to 2/3. And that's part B. For part D, we're going to plug in the values for p and q and determine whether f prime prime, the second derivative, is continuous. And the function as we approach x equals 1 from the left is 1 plus 2/3 x minus 4/3 plus x squared minus 2x plus 1, not simplified. And the right side would be 2x plus 1/3. The derivative from the left is 2/3 plus 2x minus 2, not simplified. And the second derivative is 2. The first derivative of the right side is 2/3, and the second derivative is 0. So the limit of the second derivative from the left doesn't equal the limit from the right.